In lesson 18, we're going to be talking about pricing, and then we're going to finish off the unit. I believe it's the last section. We're going to finish off with how to calculate the value of an account if it is drawing interest. So in this first one, we're going to talk about these two people who are in a partnership in a business. We have Eduardo and we have Paula. And it says that they're starting a small business making and selling tie-dye clothing. And they're disagreeing about the formula needed to add a 65% markup to the cost. And 65% markup means basically for that every dollar that you spend to make or buy that item, you want to add 65 cents to that when you sell it. So that's what a 65% markup means. If you hear somebody say they have a 100% markup, that means they sell it for double. So they add, for every dollar they spend, they add $1 to the cost. So it says, recall that B2 is the amount they pay to buy the V-neck in dollars. And so right here, that's what we're talking about. So it costs $8.79 to buy the V-neck. And Eduardo thinks that the formula to get the sales price should be equals B2 times 1.65. Paula says, no, just take what's in B2 and add 0.65 times B2. So who's right? And the answer is they're actually both right. If I take, I'm going to start with something simple. So I'm going to start with, if we just had, say, something that cost $100. So if your cost was $100, then you would want that marked up 65%, means you would want it to end up being $165. Well, let's look at what taking 100 times, we're going to do Eduardo's method here, 1.65, what does that get you? That gets you $165. If we do Paula's method, she says just take the original cost and add 65.65 times that original cost, that $100 in this case. Well, if I look at that, that gives me 100 plus 65, which is also 165. So they both get you the same result. And if we did that with the 879, we'd get the same thing. So either one of these methods is okay. And let me talk about like the reasoning behind this. In this one, this is what most people typically do because it's kind of more logical. They say, well, if I'm going to add a 65% markup, let's figure out what 65% is and add it on. So you had $100. You're going to add on 65% of that $100. And so the original plus 65% of the original gets you 165. This one does it all in one step. It takes the original amount, which would be represented with the 1 would be 100%, and the 65% all at once. So it says take your original amount and just multiply it by 165%, or 1.65, and then the 1's going to keep your original amount, and the 65 is going to add on your 65%. They both work. So now it says calculate the sales price after markup has been included. So who's right? Both. Calculate the sales price after the markup for each item shown in the spreadsheet below. So I'm going to do a couple just to show how I'm doing it, and then I'll pause and magically fill in the rest of them. So for this one, for 879, we're going to take 879, and I'm going to use Eduardo's method because it's easier, times 1.65. So if I take 8.79 times 1.65, and again, you could take 879 plus 0.65 of 879. It'll get you the same answer. Either way, you should get $14.50. Got to round to the nearest penny. It's 0.503, so I'm just going to leave it at 50. Do the same thing for the 1013. So I'm going to take $10.13, and I'm going to use Eduardo's method and take it times 1.65, Or I could have used Paula's method and done 1013 plus 0.65 of 1013, and it would have gotten me the same answer. Okay, so 10.13 times 1.65 gets us 1671. So I'm going to do that for the rest of these. I'm just going to take each one of them times 1.65 and fill in the rest of the table. Okay, so we have this all filled in for the 65% markup. Now it says 6 months later, Eduardo and Paula are doing really well with their business. They decide after the first event that prices to the nearest cent, so you have 50 cents, 71 cents, and so on, are not very practical because it takes so much time to make change for customers. So Paula decided to revise the spreadsheet to calculate the markup and then round the prices to the nearest dollar. So the rounded results she used are shown below. So for instance, we calculated we should sell this with a 65% markup for $14.50. She said, let's just sell it for $15. $16.71, she said, hey, let's just mark it at $17, and so on. $10.87 was $11. It's not always rounded up, though. The last one is, I guess, the only one that gets rounded down because it's the only one that's below 50 cents. But if any of these were below 50 cents, then you'd round it down. So $15.41 gets rounded down to 15. And then it says, although their products have sold well, Paula and Eduardo have some items that have not sold, so they decide to put them on sale. So we're supposed to first estimate the sale price of the items. Try not to use calculators or paper or pencil. See how many estimation strategies you can come up with. So 15% off would be 15 cents for every dollar. So if it's $15, I'm not going to worry too much about the estimating here, but if I take 15 times 0.15, then I'm going to get $2.25, and so that's how much I'm going to take off. So if I start with $15 and I want to discount that, then that would end up at, what is that, $12.75. And then you would keep doing that for all of these. So 17 times 0.15 and subtract that off. However, there's more than one formula that works. I said take $15 times 0.15 and then subtract it from 15. So I did 15 minus 15% of 15. Ooh, too many 15s in there. That's how I got that. But that's basically the same as like what Paula did up here with the plus. Start with the original and then add on what you want to mark up. Here we started with the original, subtract it off. There's also an Eduardo method to this. We could do it all in one step like Eduardo did. But we don't want to take it times something over 100%. So this is like 165% to add on to the cost. We want to take off. So what we want to do is we want to take this. Let me put it up here. So this is or. You could also take 15 times what is 100% after you take 15% off. So 15% off is the same as keeping only 85%. Because remember, 100% is like the whole. So if we were at 100% and we took 15% off, then we would be keeping 85%. And that gives us the Eduardo method here of we could just take 15 times 0.85. And that would be a one-step, little bit quicker process. We're going to do the same thing here. So 17 times 0.85. If you're taking it times 0.85, you're losing 15% because you were at 100%. So 17 times 0.85 gives us 1445. And then we would do the same thing here. 11 times 0.85. And it gets marked down to 935. And so on. So it says, write a formula that Paula can use in cell D2 to find the new sale price of a V-neck. Try to find more than one. So if we did Paula's method, we would do equals cell D2. So that would equal D. not D, but C2 minus 15% of C2. That would be one way to do it. The other way to do it would be just to take C2 times 0.85. And that would, either one of those would get the same thing. And I don't care which one you put on, if this question's on a test, I don't care which one you put. Whichever one makes the most sense to you, do it and stick with it. It's fine. Paulo and Eduardo have a few scarves that do not sell after being discounted, so they decide to take another 15% off. So Eduardo says the result is the same thing as a 30% discount, but Paulo disagrees. So who's right? What's the new sales price? So let's look at a different situation. Eduardo says if we take 15% off and then we take another 15% off, hey, that's just the same as if we took 30% off. So again, when you're trying to figure out things like this, don't hesitate to look at some simpler numbers to see if it works with those numbers. Because if it doesn't work with those numbers, it probably doesn't work with the other numbers and vice versa. So let's say we were originally at $100 and we took off 15%. So 15% off would be 100 times 0.85. And that would give us $85. So 15% off of $100 is $15. 15% means 15 per 100. So we took off $15. So now we're at $85. So after we have the $85, we're going to take 15% off. Well, if it was the same as before, we would take $15 off. If taking 15 and then 15 is the same as taking 30, then I should just take another $15 off. But that's not what happens. Because this has already been reduced, we only have $85 now, and we're going to take that times 0.85. So we're going to take 85% of the 85%. Well, that doesn't come out to be $15. That comes out to be, we go down to $72.25. So we don't take $15 off, we take $12.75. That's because we're starting at a lower number. So if we're starting at a lower number and we use that number to take off 15%, you're not going to have $15 off because you didn't start with as much. Another way that sometimes, so who is right? Paula was right. And then what is the new sales price? So we'll look at the scarves. The scarves were the same as the V-necks, so they were selling for $12.75. So if I wanted to mark that down again for the scarves, I would take $12.75 and I would take it times 0.85 to take the 15% off, and 12.75 times 0.85 gets me $10.84. So the answer to that question is it would cost $10.84. Another way to kind of describe this, if you're still not quite, this isn't quite working, think about to yourself, what if the store said 50% off, and then they said it's 50% of the, let me see how they would normally word that. They would say, an additional 50% off is a lot of times what they say. Take an additional 50% off. So it's 50% off. They say take an additional 50% off. Well, if Eduardo's thinking was true, when you take 50% off and then you take another 50% off, you'd be taking off 100% and you'd get it for free. But that's not the case. We know that if we start with something, say we won't do $100 this time, we'll do something easy to work with but not $100. So say we started with $40. If you were at 50% off, then that would be $20. And then if it says take an additional 50%, that means take that amount and cut it in half. So now we're at $10. So if you just keep taking 50% off, it'll get less and less, but it's never actually going to get all the way down to zero because you're going to take whatever you have and cut it in half. So the biggest thing here is two consecutive percentages, one followed by another one, is not the same as just adding those together. That doesn't work. You have to do one, then do the other. And if you're taking off each time, you'll add a little bit or you'll take a little bit less off. If you're adding to it, like if it's a bank account that's drawing interest, you'll add a little bit more each time. So in part B, we're going to look at sales tax. Rather than markups and discounts, we're going to look at the actual sales tax. So sometimes in an advertisement, you'll see, we pay the sales tax for you. What's the difference between this and a sales tax holiday? So it seems like the same. It's like, well, it means I don't have to pay tax. Wouldn't that just be the same thing? But it's not, because when it says we pay the sales tax for you, that means somebody's still paying the sales tax. When they have what they call sales tax holidays, that's like in Texas, we usually typically have those before school starts, and it's a chance where you can go buy things and not have to pay taxes on it. Well, in that case, the store doesn't have to pay the tax for you. Nobody's paying the tax. The state is giving everyone a holiday from taxes, and nobody is paying those taxes. So in this case, the store is paying the tax, whereas in this case, nobody is paying tax. Now, for you, for the consumer, it really doesn't make a difference. It's the same result, but in actuality, they are different. Okay, so it says at some events, Eduardo and Paula have to charge sales tax. This means that the total charge is no longer rounded to the nearest dollar, and they have to take the time to calculate the customer's change again. So they had these all rounded to the nearest dollar, but then lo and behold, they had to add on this tax, and it messed it all up. So for example, for a V-neck tee, they wanted to charge $15, and then with the 7.5% tax, that came to $16.13. So Paula says, hey, let's set the prices so that they come out to even dollar amounts after the tax is added. So the V-neck tee, they round up to $17. They decide to round up so they don't lose any money. So here's our spreadsheet. It says these are the amounts that they want to charge after tax. But they have to report to the state how much they charged and then how much was taxed. They don't want to give the state more than 7.5%, more than they have to. So by saying I'm going to charge $17 after tax, that means you've changed the before tax amount technically. So what we want to know is if we start with $17, if it's $17 with tax, then how much before tax. So this is called backing out of a sales tax. The mistake that I see people make is they think, oh, well, if I had an amount and I added on 7.5% and I got $17, I should just be able to take off 7.5% of 17 and get back. But you notice the price before tax is less. So if I take the amount before tax and I take 7.5%, I'm going to add on a certain amount. If I then go to the after-tax amount and I do 7.5% of that, it's going to be bigger because this is a bigger amount. So the 7.5% is based on what you're multiplying it by. And if I multiply it by this bigger amount, I'm going to take too much off. So I don't know how to emphasize this enough that you can't just take that amount and take 7.5% off. So what we have to do is we have to basically solve this formula. So we have to say, okay, the price before tax times 1.075 using Eduardo's method to add on 7.5%. We're going to multiply it by 0.075. Got us the $17. Got us the after-tax price. So what did we start with? Well, in order to get rid of multiplying by 1.075, we're going to divide by 1.075. So 17 divided by 1.075 gets you a before tax price of $15.81. So they're technically selling that shirt for $15.81, and the rest of that, $1.19 I think it is, would be the sales tax. That's what they're going to give to the state. So in the past, students have always said, could you just tell us, like, what do we have to do? So to get the pre-tax amount, if you want to kind of think of this as a formula that you can use, you're going to take whatever the full price is, the price after tax, and you're going to divide it by 1 plus whatever the rate of tax is. So in this case, we took $17 was the full price, and we divided it by 1 plus 7.5%, 1.075. And that will work every time. So you're going to take the full price and you're going to divide it by 1.085, 0.059, whatever the sales tax is, you're going to add that rate on. So that's how we can figure out the prices for these other ones. So for B2, to get B2, we would take, whoops, I did that wrong, sorry. So to get B2, we're going to take C2, and we're going to divide it by 1.075. The full price, which is C2, and we're going to divide it by 1 plus the rate, which in this case is 77.5, so it'd be 1.075. So that's a formula that she could use here. The next one would be the same, but with a 3, so this would be C3 divided by 1.075. This would be C4 divided by 1.075, and that would back us out of the tax all the way down. So the last thing we're going to do on this lesson is we're going to just kind of play around with some different things that you can do that look similar and try to figure out which one goes with which. So we're going to start with column A, and it says, what if you started with a dollar amount and then you added 0.45 times that dollar amount? What are you doing? Well, that would be Paula's method for adding on 45%. So that would be an increase of 45%. So that's this one. 0.45x is not an increase. That's less than the original amount. There's a couple different ways you could think of that. You could think of just 45% of the original, or if you're left with 45%, that means the same as if you took off 55%. So this is technically a decrease of 55%. I'm going to write these in front. I think the lines are going to get too confusing. And I'm not going to cross these out because we may actually reuse some of them. So decreasing by 55%. X minus 0.55x. Well, that's actually a more direct way of doing what we just did. Start with our dollar amount, take off 55%. So that is also a decrease of 55%. 1.45, this would be Eduardo's method of adding 45%. This would be like what Paula did, x plus 45% of x. This would be like what our Eduardo did. He started with 100% and then added 45, so it's 1.45. So this is also B. This one, remember, 1 is the original. So if we were at 1 and now we're at 3.45, what have we added? So you start with 1, and now we've gotten to 3.45. How much is added? Well, we've added 2.45. So this is an increase of 245%. Not 345%, because you already have 100% is what you start with. So this one is very similar, but it's one less. So this would be an additional, you added 1.45, so this would be an increase of 145%. This would be a increase of 55%, that's C. That's the Paula method where you start with an amount and then just add it on. Here, real straightforward, we start with a dollar amount, we subtract off 45 cents on each dollar. That's a decrease of 45%. Where's that at? J, there. And then this right here, if you are, again, we don't have x plus or x minus, we just have 0.55x. So if we're left with 55% of x, that means that they took off 45%. These $2 amount, these two have to add up to 100%. So if you're left with 55%, that means there was a 45% markdown, and so that's again J. So these two are equivalent. You could also think of it up here as there's like a 1 in front of the x, so 1x minus 0.45x gets you 0.55x. If you have $1 and you take off 45 cents, you're left with 55 cents. So that's how that goes with question 3. So it's actually the last two parts of this lesson that deal with interest. And we're going to talk about compound interest. Now, it says in the preview assignment you worked with simple interest and compound interest. So what's the difference between simple interest and compound interest? And the difference is with simple interest, you just add the same amount each time, or take off depending on the situation, but usually add. So you add the same amount every time. Or you add the interest on the original amount. So like if you put in $100 and you had 10% interest, then every single time it compounded, you would add $10. So you'd add 10% of 100, $10. 10% of 100, $10. 10% of 100. Compound interest, if you have compound interest, they don't work like that. They take it and it's kind of like with the 15% discount and then another 15% discount. You go off of what you had after the interest. So with compound interest, you actually gain, let me add that here, you gain interest on your interest. So each time, if you're adding to it, you add a little tiny bit more and more. A lot of times it seems like, what's the point? It doesn't seem like it's making much difference. It's a few pennies here, a few pennies there. But when you talk about, larger amounts of money and or a longer time period, it can make a huge difference. So let's look at this a little bit. It says we got a $1,000 principal. That's how much you're putting in. Principal just means how much you're putting into the bank, into a certificate of deposit with a 5-year term that pays 2%. Okay? So this means, and the compounding period is 1 year. So I'm going to write down a couple things. The principal we usually represent with a P. So P is $1,000 in this case. 5-year term. The terms, we usually use a T for time. When in this case it's 5. 5 years. Then it says it pays a 2% annual percentage rate, APR, how much you earn each year, annual percentage rate. So the rate, we usually call this R. We don't want to put 2%. We want to put that as a decimal so that we can work with it. So 0.02. And then the compounding period is 1 year. That means it gains interest at the end of every year. Now, we ran a little short on time because of starting late. And this is the first time I'm recording this, so if you're listening to this in a later class, we may be getting to it. But the first time I recorded this, we ran short of time because of Hurricane Harvey, and we're not going to do Unit 19. And so, but in Unit 19, it talks about what you do if the compounding period is more often than 1 year. So what if you're going to compound every day or every quarter or every month? That would change our formula a little bit. But we're just going to do compounding period of a year here in Unit 18, and that's the last thing that we're going to work on. So how much will you have in the account at the end of the first year, the second year, and so on? So 1 year, we would take $1,000, and we would take that times 1 plus 0.02, and that would get us our amount accrued, because 1.02, or let's write it more like what Eduardo had it here. So this is kind of the Eduardo method here. We're going to do 1.02, and that would get us how much we have total. 1.02 keeps our original amount plus adds on 2%. So that would be $1,020. So they gained $20. Now if this was simple interest, the next year they would just gain another $20. It'd be $1,040, but this isn't. This is compounded interest. So instead of adding 20 bucks on the next year, we're going to take this 1,020 and we're going to take it times 1.02. So 1,020 times 1.02 gets us $140.40, or $1,040 rather, and 40 cents. So we didn't just add on $20, we added on $20.40. Again, doesn't seem like much, but it's only been a couple years, and it's only $1,000. And I know you say only $1,000, but we're talking about people who invest a lot of money. That's not a lot of money to them. It's a lot of money to me. But if we've added 40 cents, and so now we're gaining interest on not just the original $1,000, but we're also gaining interest on that $20. Same thing here. Now we're not going to just gain interest on $1,000. We're going to gain interest on $1,040.40. So 1040.40, and take that times 1.02. So 1040.4 times 1.02, and we get $1,061.21. So now, instead of just adding $20, we've added on, we've added on $20.81. So here it was $20.40, now it's $20.81, and we just continue like that. So each time you add just a little bit more than the time you did before. So it says, can you determine the amount in the account at the end of the 5th year without having calculated the 4th year? And the answer is that we can if we try to go back here and figure out a pattern and maybe come up with a formula here. So what we did is we took $1,000, we took it times 1.02, we got an answer. Then we took that times 1.02, got an answer. Then we took that times 1.02, got our answer. So every time we've just taken it times 1.02 again. So let me show you how this works. So like right here, if I wanted to, I could have taken 1,000 times 1.02 and then taken it times 1.02 again. 1,000 times 1.02 times 1.02 would get you $1,040.40. So each time, yes, we were taking the result, but we didn't have to stop at the result. And what we're essentially doing is each time just multiplying it by 1.02 one more time. So for this one, it's a little messy here, but we could have started with 1,000, and to get to the 3rd year, we wouldn't have had to get the intermediate answers. We could have done 1.02 times 1.02 times 1.02 because it's 3 years, and we would have gotten $1,061.21. So first, let's look at the arithmetic of this. What do we call it when we take the the same factor and just multiply using that factor over and over and over again. For instance, what do we do with, say, let me do a smaller number so it's easier. So say we started with 3. If I said I wanted to do 3 times 3 times 3 times 3 times 3, would you write it like that? Or would you, if you remembered, write it as 3 to the 5th? Because that's easier to do. So if you look at this, each time you're multiplying it by that many times. So in essence, we are, to get this final amount accrued, we're starting with whatever the principal is. Let me write it with this problem instead of in general. So for this problem, we start with the principal, which is $1,000, and then we multiply it by 1 point and then whatever the rate is. So the rate here is 2%. So if it was a 7%, we do 1.07. If it was 3.2%, we do 1.032. And then we multiply that 1.02 by as many years as there are, or we take it to the power of as many years as there are. And that would get us the year. So again, I want to do it general for this problem. So this would be the number of years. So for this problem, the 1,000 is going to stay the same because that's the principal. The 1.02 is going to stay the same, but the time can change. So 1 year, 2 years, 3 years, and so on. Now, if I wanted to write that formula in general, this is the formula that I would have. The 1,000, remember, is the principal. That 0.02 was the rate. So what we do is we take 1 plus whatever the rate is. So again, if the rate is 6.7, we would do 1.067. If the rate was 15%, we'd do 1.15. So whatever the rate is as a decimal, I put in there. And then up here is the time. And this formula you do not have to memorize. Just like on the review, it's listed at the top of the problem. It will also be listed at the top of the problem. You don't have to memorize it. You just have to understand what it means and be able to put the numbers in to calculate your amount accrued. Okay? So it says develop an equation for the total amount accrued in a CD with annual compounding after n years if the principal is 1,000. Okay, so they used n here instead of t. So I apologize. I don't like n because we use n later for how many times it gets compounded. So we'll just change this. T is more common. We'll say for t years if the principal is 1,000. Okay. So now we're going to finish up Unit 18 by just continuing with this compounding interest formula. And we've actually cheated a little bit and answered a couple of questions in this section already, so this won't take us too terribly long. It says, how would you revise the formula that we had before if we had $50,000 to put in the CD and the bank was paying 2.5%? So if that was the case, excuse me, I have the hiccups. If that was the case, the amount accrued, you would start with $50,000, and on the inside, instead of 1.02, you'd have 1.025. Make sure you always shift that decimal over 2 spots. If you shifted it over just 1 spot, you'd be giving yourself 25% interest, which would be fantastic, but not very realistic. And then compounded annually, again, we're going to use T. Every time we add a year on, we multiply what we had before times another 1.025. So it says for number 2, it's generally when your CD term is up, you can continue to leave the money in the account, but the bank may change the APR. But let's assume the bank doesn't change the APR. So use the formula from question 1 to determine how much you'd have in your account after 20, 50, and 100 years. So this looks very similar to what you'll see on the review in the test. So to get after 20 years, you're going to start with $50,000. And then you're going to multiply that times 1.025. And since it's 20 years, you're going to take it to the power of 20. This one, you're going to take 50,000. I'll just write all these down and then I'll calculate them. 1.025 to the power of 50. And then 50,000, we're always going to start with that 50,000. It's just we're going to tell it, I'm going to take it times 1.025. In other words, add 2.5% to whatever the current result is if at 100 years. So if you are not familiar with this, let me just, I think we've done this before, but just in case, remember that this power, if you're trying to figure out how to do that, on most calculators, you would type in your 50,000, and then you could do times 1.025, and then for power, there's going to be one of two buttons. It's either going to look like that, or it's going to look like a to the power of b, or it might be x to the power of y. These can be different variables. So it could be a to the power of b, b to the power of a, x to the y, y to the x. These are just saying it could be any numbers in here, so they could use any variables to represent that. Or you'll have this little caret sign, they call it, which means like up with the following number. So you would do that, and then you would do the 20. So that's how you do the exponent button on your calculator, because you sure don't want to multiply by 20 or by 1.025 20 times by hand. So let me get this out of our box here. So the amount accrued, I'm just going to take again 50,000 times 1.025 power 20, and I get $81,930.82. And that is certainly not simple interest. Simple interest would just add on $250 each year, and $250 for 20 years would get you an extra $3,000. And in this case, you've made almost $32,000. So it definitely, this is a good illustration of how, I'm sorry, it's not $250. It would add on $1,250 each year. But even at that, if you take that times 20, that only adds on $25,000, and you can see here we've added on nearly $32,000. So as you get bigger amounts and longer times, it makes a huge difference. Simple interest would have only gotten you to $75,000, and you're at almost $82,000. So this one, if I do the calculation, 50,000 times 1.025 power 50, and you can just do this all in one step across your calculator, you're going to be at $171,855.44. Again, 50,000 times 1.025, or 50,000 times 0.025 gives you $1,250. So if you did $1,250 for 50 years, just simple interest, you'd only be at $62,000 added to your original amount. So 62,000 plus 50, you'd be at $112,000. Well, we're not $112,500. We're not at $112,500. We're at $171,855. So this is where that adage probably comes from, the rich gets richer. If you have money, you can make money off of that money. And so this compounding, if you're able to leave $50,000 sitting somewhere for 50 years, it just sits there and makes $121,855 for you just by not touching it. So now let's see what we're at 100 years. So 50,000 times 1.025 to the power of 100 gets you 590,685, and then watch your rounding, it's 0.8176, so that'd be 82 cents. 0.817 would round to 0.82. It asks here in number 3, is your formula from question 2 linear? No, this is definitely not linear, because it's not going up by the same amount each year. Now, we can't really compare 20 to 50 because it's hard to, because 20 goes into 50 2.5 times, so that's a little hard. But if this was increasing by the same amount, at 0 years, you're at $50,000. Add just another row to the top of our table here. So at 0 years, you're at $50,000. Well, from 0 to 50, you gained 121,000, and then from here to here, you gained almost 420,000, 419,000 roughly. And so it's not going up by the same amount each year. If we graph this, it would not be a line. In fact, it would be kind of like we saw on that scatter plot. It would start out kind of slow, and then it would increase quickly. It's called an exponential growth. So it's the exponent that's getting bigger, and so it makes it, that's not even very accurate. Let me try again. It starts out slow, and then it goes like this. So kind of flat at the bottom, increasing just a little bit, and then it goes up. Now it says write a general formula that can be used to find the amount. We already did that, but let me just reiterate our general formula that you're going to be given on the test. You don't have to be able to regurgitate it. You just have to know how to use it. And again, I use T for the number of years. So 1 plus R to the T. So principal, that's how much you put in to begin with. 1 plus the rate. Make sure you switch that to a decimal, and then T is how many years it is, and that'll get you the amount. Then last little note here, it says, remember that in actuality, CD rates will normally adjust at the end of the term, so forecasting 20, 50, or 100 years in the future is a little bit unrealistic. However, investors can purchase municipal bonds that last for years. The Nashua Telegraph that's in New Hampshire reported a case in 1981 where a man found a $100 municipal bond that had been accruing interest at 10% for 110 years. So let's look at what that would be using our formula. So if this was only compounded annually, but it was a $100 bond, so his principal is $100. Rate is 1.10, which is a pretty high rate for something that you put in the bank. You don't usually earn nearly that much interest on it. So 1.10, and it was 110 years, so your T is 110. So watch all your ones and zeros here, but it'd be 100 times 1.10 to the power of 110. And this is the amount that this comes out to be. It is 3,574,335.94. And so that $100 bond over 110 years turned into $3,574,335.94. Again, that's because you compounded on the interest. You added interest to the interest, and you left it there for 110 years, and this is the result. I actually have read about this, and if I remember correctly, I think what happened, this would have bankrupted the city because this is just a small town in New Hampshire. And so they ended up coming to some sort of a settlement because he didn't want to bankrupt the town. And so, but technically, this was the value of that municipal bond after sitting for that many years. So anyway, that will be the last thing that you'll see. Again, if you're in my class when I recorded this, which was in December of 2017, this is our last unit. If we hadn't been affected by Harvey, we would have done Unit 19 also. But this will be the last thing that you'll see on the final. Will be a table like this with the dollar amount. It'll give the formula at the top, and you just have to be able to do the calculation. So you put in your principal, 1 plus the rate, to the t and get the amount accrued. So make sure you know how to use this formula. It's pretty quick and easy to do on your calculator as long as you know what numbers to put in. If you get the numbers in here wrong, things are going to come out with crazy answers, and you're going to know it's wrong, and it's going to be frustrating to try to figure out what's going on. So make sure you know how to use that formula.